Not much left over. Just give me a second. Yeah. So talking about support vector machines, and I copied these images to your notes for understanding kernel function. There is a little bit remaining. So the kernel function, there is no one function, one kernel function generally. I don't know why it came up. So there are many kernel functions available. You can use one of them, and strictly speaking, no one knows which one will work better on a given data set. All you have to do is you have to try out different functions. One of them will work better. Kernel functions. So the first one is linear kernel. So linear kernel works like this. It will try to do a dot product on any two support vectors. So linear kernel k of xi xj, what it will do is it will do a dot product. So xi into xj. So what is the meaning of dot product? So let me tell you one more thing. So where xi and xj are support vectors. So what it does is, let's say 1 to 1 comma 2 comma 0. Let's say, or let me give you a two-dimensional point. Let's say if 1 comma 2 is one support vector, and let's say 2 comma 3 is another support vector. So let's say this is xi, this is xj. So what will be the dot product? Xi into xj will become, so you multiply the corresponding elements and add all of those terms. So what it means is you multiply 1 and 2, 1 into 2, and you multiply 2 into 3, 2 and 3. Always multiply the corresponding elements and add up all those terms. So what happened is it became 1 into 2 plus 2 into 3. 2 plus 5, which is 7. So this is how dot product will work. Linear kernel will work on dot products to create higher dimensional values. So that is the first one. Then the second one is Gaussian kernel. So kernel of xi comma xj. So Gaussian kernel simply means that we have to use normal distribution formula. So that's why what happens is Gaussian kernel will look like this: e power modulus of xi minus xj by 2 into sigma square. So if you remember if you remember the normal distribution formula, 1 by 2 pi square root of 2 pi sigma square into e power x minus mu whole square by sigma square, e power half into. So this is the normal distribution formula. We simply use the similar formula. Instead of x minus mu, we are just replacing it by xi minus xj, and we are removing this constant. This is a simple constant, so we are not using it. So that is how Gaussian kernel will look like. So this is another kernel. Again, every kernel function, what it does is it will convert the data into some other dimension. That's all it does. So each kernel is going to convert the data into some other format, some other dimension. It will keep on adding the dimensions. Polynomial kernel. Here k of xi xj is equal to xi transpose into xj plus 1 whole power p. Well, where p is the power that you want to use. You can use square, cube, anything you can use here. So xi transpose xj is nothing but it is a dot product. So you are using the same dot product. So xi transpose xj means actually your vectors will look like this: 1, 2, 2, 3. That's what we are using. We transpose one of them. If we transpose one of them, it will become 1, 2 into 2 into 3, 2, 2, 3. So if you multiply 1 into 2 plus 2 into 3, that's what you're going to get, which is nothing but 1 into 2 plus 2 into 3 that we did in the dot product. So there is no difference between the dot product and the this kind of a formula, which is transpose of one variable and multiplied by the another variable. This is a matrix notation. This is a vector notation. So if you keep an arrow here, it will become a vector. These are nothing but these are matrices. So that is the only difference. So this part is same. You are just taking a power of p, which means we are simply getting the power of the linear kernel, some polynomial function of a linear kernel. That's all we are doing in the polynomial kernel. So each kernel will have a different properties. Because of those different properties, each kernel will behave differently after you project your uh, low, low dimensional space into higher dimensional space. That's the technical terminology. If you are projecting your lower dimensional data into higher dimensional space, then one of these kernels might work. Now, which kernel will work? No one can tell. It is only by trial and error you have to try to find out which kernel is good. That is another reason why I did not go into the mathematics part of all these kernels, because it is useless. Even if you know about the mathematics of it, there is no reason, no value of it. So that's why I'm not going into those things. So that is about the support vector machine. Let me reiterate the points again a little. So there are three kinds of support vector machines. One is maximum margin classifier. Second is soft margin classifier, or it can be called as support vector classifier. Then the final one is support vector machine. Now, maximum margin classifier, all it does is it tries to find out a line or a hyperplane which will separate any two classes, and by keeping maximum margin between the hyperplane and the data. From the data, there should be maximum margin. So that's all maximum margin classifier says. But what it also says is it will say there is no misclassifications allowed. So maximum margin classifier is more like an idealism. I don't want any misclassifications to happen. That's all it is. That's all. That's what it is saying. Now, because maximum margin classifier is saying like that, because it is saying I don't want any misclassifications, it is very difficult to find a proper hyperplane. In theory, we can always get, but in practice, what happens is you have to always project your data into higher dimensions. and try out the maximum margin classifier. At some higher dimension, you will be able to definitely able to separate your data. But problem is, it is very difficult to always project the data into that much higher dimensional space. We'll still get some errors. So the second thing is support vector classifiers. All it gives is an extra error function. With this error function, what we can do is we can define the maximum error rate that I may get. And error means either it is a misclassification based on the hyperplane or based on the margin. If the misclassification is on the margin, your epsilon value, whichever is the error that you're calling, is between 0 and 1. But if epsilon is 0, then there is no difference between between support vector classifier and maximum margin classifier. If epsilon is between 0 and 1, then your data points are misclassified according to the margin. And if epsilon I is greater than 1, then you are on the wrong side of the margin. So you have to add this error to the final total. So your classification error is nothing but sum of all these errors, and you can give a maximum value, an upper bound for this total error value, which you can configure as a tuning parameter. And then finally, we talked about support vector machine, which is nothing but support vector classifier plus something called kernel trick or kernel function. So what this kernel function will do is something like this. It will project your lower dimensional data into higher dimensional space. So if you do that, there will be more possibility that your data is linearly separable. When I say linearly separable, just by drawing a line or a plane or a hyperplane, I will be able to easily separate the data into two parts. Two different classes. So that is what it is when I say linearly separable. And we talked about the kernel functions just now. There are 3 kernel functions, and in reality, we'll never know which one will work very well. All you have to do is try out different kernels and see the accuracies, train test errors. That's all we can do about kernel functions. So that is about the support vector machines. So let's go into the problem. So let me clear the output. The data that I'm going to classify this time is a little different because I know that we are getting bored with the iris dataset, which we are doing many times. So this is a much more tougher problem that I'm going to solve this time. The problem that we are going to solve today is somewhat image classification. It's a beginner kind of an image classification. We are not going into deep about this image classification at this moment. In fact, we are not going into image classification in this course at all. But this is a kind of a taste. This gives a taste of how image classification works. And image classification is known to be highly nonlinear, very, very nonlinear. The reason is it's very difficult to separate. Let's say, let me give you an example. Let's say I have cats, images of cats. No, it's very tougher to say, let's say, this looks like a tiger to me. This doesn't look like a cat at all. And some of the cats are fine. I mean, I can easily classify. But some of the images, they are not really only cat. There is a cat and a snake here. I don't know. I mean, the problem here is when I am doing the image classification, I may have so many noises, or some, for example, this is very close up look compared to this one. And this is much more closer look compared to this one. So there are different angles in which the image can be present. Whether it is, the background will be different. The angle at which you took the photograph, all of these are different. So because of this, image classification is one of the toughest challenges in the field. And this we can solve only using something called deep learning, which is not the subject of this course, but still we are going to do it. We are going to do something like that, similar. This doesn't have as many problems as the images I showed you, but it still has some problems. So for example, the problem that we are going to solve is here, classifying the handwritten digits. So let me load the imports. It was imported. Don't worry about this one. This is the deprecation warning, the simple warning. And I loaded the digits data set. What is this? This is something like a handwritten digits. Someone wrote these digits, scanned the images, and loaded it into this data set. So if you load this data set into X and Y, let's say I show, if I try to show the X, all you get is zeros and ones. Now it is very difficult for you to identify what this 0050, whatever it is, all these numbers mean. So if you have at any point, if you have learnt any of the computer graphics kind of a subject, what you learn is every data point in the image, every pixel in the image. So each image is divided into small dots called pixels, and each pixel will have some color. So the color is determined by RGB values. R is red, G is green, B is blue. So any color that you see in any image that I just showed you is simply a combination of all these RGB values. So whatever you are seeing, these numbers are nothing but RGB values, nothing else. Very simple. Whatever you are seeing is RGB values. But unfortunately, you are not trained to look at this kind of image. In fact, even if you are trained, I really doubt, just by seeing the image, you cannot seeing these numbers, you cannot visualize what is happening there. So for example, the first data point, first element is like this. Can you identify what is the image? You can never identify what is this image. It is very difficult. But unfortunately, computers are more trained to understand numbers than anything else. So if you give an image, computer can only interpret using these numbers. But we are not a computer. So what we should do for this? So what happened is, so every image, case study. Digits recognition. So we're trying to recognize some digits, and it's not a difficult problem once we go into the support vector machine, because support vector machine is going to go very non-linearly, or it will project everything into higher dimension and try to solve the same problem in linear way. So let's try to identify what is this, understand what is this numbers. So what happens is your image will have some length and some width. So for example, in this case, each image is having 8 as length, 8 as width, which means 8 pixels as length, 8 pixels as width. Now, what this guy has given us is, so every point, so 8 by 8 means it is a matrix. It's a something similar to a table of 8 by 8 rows and 8 columns. So you'll have something like this. 1, 2, 3, 4, 5, 6, 7, 8. Similarly, there will be 8 rows. 1, 2, 3, 4, 5, 6, 7, 8. So your image is having some number of pixels organized in a tabular format. So what our image is, it is an 8 by 8 image. When I say 8 by 8 image, there is 8 rows of pixels and 8 columns of pixels. That's what it means by 8 by 8 image. Similarly, these days we'll get I don't know, 1650, something like that. What is the current size of the image? Image dimensions. I forgot what is the standard size of image. Standard image dimensions. So these days we are having a higher dimensional images, something like, yeah, this is the image 2048 by this one, 2048 by 1536 is the standard image size that we are using currently in any any laptop or any mobile phone that you take a picture. 2048 by 1536 is the standard image size. So 2048 by 1536. But currently we are not taking such a big problem. It is a subset of this problem, very small problem, small subset of the same problem. So what we are taking is 8 by 8 image. 8 by 8 is the smallest image, very small image. So using this 8 by 8 image, what we are doing is every cell in this 8 by 8 grid will have some numbers. Let's say 5, 50, 250, 10, something like that. Some numbers will be there. Each number will represent some color. So each number will represent some color. So finally what happens is, if you put them all of them in a grid, you will be able to visualize some image. Now for us it is an image, but for a computer it is all a set of numbers. That's how I am showing here. Now the same image, if you want to see, then what you can do is you have to, so what happened is, this guy 8 by 8, 8 rows and 8 columns, which means there are 64 pixels in this entire table. So for every image there will be 64 numbers. For every image 64 numbers. So what we did is, here what he did is, all the 64 numbers he has flattened it. He did not create a grid, he has flattened it and gave it to us. So to show the image, all I have to do is I have to convert this into some kind of a grid, which is this 8 by 8 grid, and then show the image, visualizes the image. So that's what I am doing here. I'm getting a random number. Do not worry about the random number for now. I'm just selecting one random picture. So x dot shape of 0 means number of rows. So from 0 to number of rows, I'm getting a random value. What it means by random value means I'll get a random image. For that image, what I'm doing, I'm getting that image x of rand, which is a random image that I'm selecting, and reshaping the data into, instead of this flat format, I'm converting it into this kind of a grid format. So how the flat format happened is, you take this likewise this entire row, but you don't keep the next row in the bottom. What he kept is, he kept on the list of data points here itself. That's how he has flattened out. So to unflatten that, there is something called np.reshape or reshape method. Sorry, np is not required here. Reshape method of 8 comma 8. I know that it is 64 pixels are there. I have to convert that 64 pixels into 8 by 8 image, 8 by 8 format. That's how I am doing. And then saying image dot show. And also, so for every image, there is also a target value, which is the, so there is an image and there is a label also. That label is having what is the number that image is showing. Without any, without any label, you will not be able to classify. So let me show it. Which number it is? How does it look like? Some shape you are seeing? It is somewhat like 0. Okay, are you guys clear? So there is an image and there is a label also. This is actually 0. That's what he is saying. There is an image and there is a value. So if I run this again, I'll get another random image. This he's saying it as 2. The actual value is 2. The image corresponding image for this is this one. And you can see it is quite difficult to find out what image is what. The images are very low resolution. 8 by 8 is definitely very less resolution. So it is very difficult for any human. I don't know what is this. This looks like somewhat 8, but it also looks like 2. It also looks like 2, or I can also say it is 8. So it is like this. I can say 8 or 2. Sometimes it is very difficult to identify what image it is. This is 0 definitely. This is also 2. And this he is saying 4. I don't know how how it is 4. Maybe, I mean, I can easily say, but sometimes it is very difficult. Some numbers are even more difficult actually, some images. So every time I run this, because I am taking a random number, I'll get a random image. This is 7, he's saying. Maybe it is 7 like this. I don't know. Something like this. So all these images are very difficult to identify. Now the question is, given any image like this, can I predict using support vector machine? Are you guys clear with the problem? Is it interesting problem to solve? This is saying 9. Again, it is very difficult to find out it is 9. For human, it definitely is a challenge to identify which number it is, at least. This is 0 anyway. This is 7. I don't know. This might look like 7. Yeah, this is 6, 4, Somewhat, I think you are also trained to understand this data. Are you guys clear or not, Vijay and Abid?
Yes, Sandeep.
Okay. So using this, we have to take, we have to predict. So what I'm doing is, first I'm doing a train test split. As usual, there is no difference whether it is an image classification or any other classification that you are going to do. The train test split and all those grid searches and all those things will still be same. So let me do the train test split first. So I got train and test data. Then I loaded the SVM classifier. SVM classifier is also here. sklearn.svm is there. You have to import this. So all I am doing here is I am doing a parameter search again. How I am doing? I am giving a list of kernels. These are the kernel functions. Linear function is one kernel. RBF is nothing but radial basis function, which is nothing but the Gaussian kernel. And if you remember, there is a sigmoid function in logistic regression that can also be used as a kernel function. I don't know which one works very well. Maybe RBF works very well, or maybe this time linear works very well. I don't know. So I took all of them in a grid search, which means one of these will work very well. So grid search will pick that one. And the C, if you remember, the C is nothing but the total error, sigma of error, maximum error that I can get. I gave some random values, 0.001, 0.003, something like that I gave. Now within this grid, it has to find out what is the best parameter. So using this grid search, I'm fitting the training model and doing a prediction on the training dataset itself and getting a final accuracy of the training dataset. But remember that this is not what we are interested in. We are interested in the test dataset accuracy. So if I run this, it's going to run the grid search. It will take a little time because it has to try out all the parameters. Let's wait for a minute. So it is saying it has run the grid search, and finally it is saying the accuracy on the training data set is 98%. And let me show this one, best estimator. So what is the best C and best kernel it is found? So it is saying kernel is linear. So it looks like linear kernel is working very well for this data. It is more than enough, it looks like. And the C value is this one. That's what it has found out. Then I'm doing a prediction on the test data set and finding out the accuracy of the test data set. You can see test data set is having 99% accuracy, which is looking really good. But the point is it predicting properly really? So if you see, the classifier or the grid search never saw training test data set. It only saw the training data set. Now on test data set, it is saying I am able to predict 99% properly. Let me see if on test data set it is getting properly or not. So what I got is, from the test data set, randomly I'm picking one number and showing that image. Now here I am showing that image number and then saying reshape of that random value on the test data set. From the test data set, I am showing some image and saying what is the actual value, what is the predicted value. Actual value is nothing but it is coming from the Y. Predicted value is nothing but I already have a test prediction. That this is a test prediction. That test prediction, from that I am getting the random value, whatever random value I picked. For that I am getting a label. Let's see if my actual value and predicted value are correct or not. So for example, I ran now. So it is saying image number 144. Actual value is 5 and my prediction is also 5. It looks like it is 5. Yeah. If you see properly, I don't know, it looks like 5. Something like this it is coming. It is looking like 5. So my prediction is correct for this image. Let's see some more images. If I run this again, because it is picking randomly, it will pick, I'm sorry, I unshared. If I run this again, it will pick another image again and it will try to predict. So actual value is 0, predicted value is 0 and the image is like this. Yeah, it looks like 0, so prediction is also correct. This one is a little difficult to predict if you see, but yeah, approximately it is looking like this, something like this. So approximately I can say it is 1, and that's what is the actual value as well. So my prediction and actual value are same. Again, if I run this again, this time it is somewhat weird, but it looks like 8 to me. And here it is also saying actual value is 8 and predicted value is 8. Again, my prediction is correct. I'm just trying to find out if there is any prediction that is wrong. Sometimes it may go wrong. Let me run multiple times. If it gets some wrong prediction, because the accuracy is not 100%, it is 99%. So at some point it should give me some wrong value. This is 3 and 3 is also fine. I hope you got a clear picture. Somewhere I should get a wrong prediction also, because my accuracy is only 99%, not 100%. So except that I am not able to get it. I just wanted to show where the wrong prediction will go. No, it's not coming. That's okay. But my predictions are almost correct. I hope you understood how image classification can be done in general. It's not a total class on image classification. This is more like an introduction. It's a very basic introductory class on image classification. But you got a taste of how images can be classified. How do you identify, how computer identifies an image? Are you guys clear? I hope this is a better example for you to understand image classification. Any questions?
No questions, Sandeep.
No, Sandeep.
Okay. Hope you enjoyed this problem. We'll take a break and we'll come back at 7:20 and we'll start another topic called clustering. Okay. Okay, then we'll catch up at 7:20 or 7:25. We'll come back. Okay. I need some break actually. We'll come back at 7:25.
Sure, Sandeep.
Are you, are you guys back?
Yes, Sandeep.
Yeah, I'm here, Sandeep.
Yeah. So Vijay, if you want to take rest, you can leave. You can. I'll provide you the video.
Okay, thank you, Sandeep.
So that is about the support vector machine. Do you have any questions for support vector machines?
No, I'm clear, Sandeep.
So we'll go into another topic called clustering. So we'll go into the basics of clustering today. So what is this clustering? So imagine that you're blindfolded and you're given some coins, say so let's say imagine you are blindfolded, you don't know what you're seeing, and you're given some say coins. Let's say I don't know US uses any coins, but in India, you have 1 rupee coins, 2 rupee coins, let's say 5 rupee coins. And let's say 10 rupee coins. You have coins of different sizes and different shapes and weight and everything. So what you're given is all these coins, maybe hundreds of coins, and you're asked to let's say you're not even blindfolded, you don't know how to read numbers. So each coin will have some number and you don't know how to read. Now the question is, how do you so the point is, you don't know what is what, but each coin has different properties, different weight, different thickness, different shapes. Each coin has different properties of the coin. I mean, the metal that it is used, the color. There are many things that are different, not just the number that is written on the coin. Now imagine that you don't know how to read, and you want to sort out different coins. So let's say uh, I want to group the coins into all the coins into 4 different groups. Because I cannot read, I don't know what is this first group has, what second group has, what third group has, what fourth group has. What I mean is, I cannot say this group is only having 5 rupee coins, or this group is having only 10 rupee coins. Instead of rupees, you can think of as a dollars also. That's fine. The point is, each coin is having different properties, and I want to group them together, and still I cannot label them. When I say I cannot label them, I cannot say easily that this is a 1 rupee coin group. I can simply say this is one group, this is second group, this is third group, this is fourth group. and I don't know what it has. So this kind of a problem is called clustering, and this is different from the regression and classification that we have learned till now. So what clustering does is it just groups similar items together. That's it. It doesn't do anything. Now, what is the purpose of doing all this grouping? So the idea is, let's say there are people who did some fraudulent credit card transactions, and there are many other people who did not do any fraudulent transactions. So tomorrow, if you swipe your card, every time you swipe, the bank has to identify whether you're going to do any fraud or you're not going to do any fraud. To identify this, you have to find out some properties of the person, whether his age or his credit history or many other factors, and try to group all the people who do not do fraud and all the people who might do fraud. But in this case, you will not have a labeled data. You cannot label the people saying this guy will do fraud. You don't know. So in these cases, what you do is you do not have any y variable. You do not have any label saying he will do fraud, he will not do fraud, all those things. But you have to group people together according to the similarity in their characteristics. So this problem is called clustering, combining the data into groups which are having similar characteristics. That's all I need. If I have similar characteristics, all those people will go into similar groups. Okay, we are just grouping things. We are not even classifying. We are not labeling things. So there is a difference between clustering and classification. Clustering is you have some data, and using some characteristics, what you do is you group all the set of people with some similar characteristics together. You say this is a group, but you will not give it a name. This is another group. But in classification, what you do is you will give a name. For example, this is a safe loan, this is a risky loan, or this is a say this is a what do you say? This is a cat, this is a dog, this is a cup, this is a bottle. So if you name the things, then it will become classification. If you do not name but just group the things together according to their similarities, then it is called clustering. We'll get into a problem once we once we understand what is this classification. But for now, just understand that it is simple grouping without naming things. Are you guys clear?
Yes, Sandeep.
Simple grouping, that's it. This is one group, this is another group. What is the name of the group? I don't know. I'll not give any names to the groups. So when you are doing clustering, we don't use the y variable. The y variable is something that I don't use at all. So, and it is an example of unsupervised learning. What is this unsupervised learning? There is no training actually. So until now, all we did is we are training the model and testing the model. But in unsupervised learning, there is no training, because if there is a y variable, I have to say that for this kind of data, this is a y variable. For this kind of the data, this is a y variable. I have to give the y value for each of the data point. If I give like this, computer will identify this is how I can classify, and tomorrow for any new data it is going to predict properly. That's why that is called supervised learning. You have to train and test. Here there is no training. All you have to do is give all the data to the machine learning model. It will try to group the things. Are you clear so far?
Yes, Sandeep.
Okay. So why is this useful actually? So many times this is useful because you want to group the things, but you don't know what is the output. You just want to do a grouping. Can you give me an example why you have to group but you don't have to predict anything? Any real world example that you can give? Just think about it a bit. So let's say you have a lot of customers. You have lost a lot of customers, and you want to understand how the customer buy. I mean, what groups of customers are there? So there are few customers who will always go and buy only dairy products. There are a lot of customers who will buy all the grocery items. Some set of customers will come to you only for buying maybe some bakery items. So you want to understand what groups of people are there, but I cannot identify by names. First I have to just group them. What are the kind of data, what are the kind of customers I get? I just have to group them. What kind of groups are there? After getting the groups, I have to further analyze just by looking at the data to see if this group means bakery purchases, or this group means people who are purchasing groceries. Are you clear? What is the example?
Yes, Sandeep.
So to group the things, we need some kind of similarity measures. So again, we are going to something called similarity measures, because I have to say that these two people are same. So why do we need, let me give you a real-time example, which I generally do in my day-to-day work. So the idea is I have to show an ad. So there is an online advertising industry, and this online advertising industry works like this. If you visit a website, so in that website you'll see some advertisements at the bottom, at top, somewhere you'll see all the advertisements. So what you're supposed to do is so the advertisement industry works like this. When you visit any website, the advertisement that you are going to see should be very, very relevant to what you do. For example, if you are interested in sports, maybe an advertisement showing a sports shoe is much relevant to you compared to any advertisement that is giving any food related product, because your interest is in sports. Or let's say you're interested in uh, buying a some of the health products, showing you some health product like any whey protein or something is much more better, and you're going to buy that product more than any other product. Now in these cases of in these situations, what I'm supposed to do is, if I want to advertise some product, I have to group people based on their interests and say which group is more interested in the my advertisement. I cannot classify each person saying this guy is going to see the ad, this guy is not going to click on the ad. That is impossible for me. What I have to do is, based on the similar interests, I have to group the people and find out a group which is more interested for my products. That's all I have to do. So again, I have to identify this using clustering. So there are many clusterings that are available. Before going to similarity measures and all, let me talk about clustering a bit. So clustering has many techniques. It's not a single technique. So, but at a high level, there is hierarchical clustering. And non-hierarchical clustering. And hierarchical clustering is divided again into agglomerative. Don't worry about the names. This is one of the easiest technique that we are going to learn. Agglomerative clustering and divisive clustering. And in non-hierarchical clustering, there is random partitioning, and the technique is called K-means, and initial seeding. So in this entire thing, divisive clustering is not possible or not feasible solution because it will take a lot of time. And initial seeding we are not going to learn. So what we are going to learn is agglomerative clustering and K-means, which is random partitioning. Okay, these are the techniques that I can use to group things together. So the first technique that we are going to learn is agglomerative clustering. One more thing. So within this agglomerative clustering itself, there are multiple techniques. The first technique is called single linkage. Single linkage. Then complete linkage. There is word linkage. We'll talk about all these things, just naming things. And average linkage. There are many such techniques. So let me write only these four for now. There is even median linkage, average linkage, centroid linkage. There are many techniques. So let me talk about agglomerative clustering first. Sorry, agglomerative clustering. So what this agglomerative clustering does is, it initially assumes that all the data points, each data point is in its own cluster. Initially, we assume that each data point is in a different cluster. We assume each data point is in a different cluster. Then we keep merging the clusters using some methods. Merging the clusters by using some criteria. Okay. So for example, it will be like this. Let's say your data points are like this. So what this clustering will do is, it will try to identify the similarities in the data points. So for example, each one is in a each data point, whatever point I have given, is in a different cluster. What it will do is, it will try to, we will try to combine these two data points into some cluster, we should combine these 2 points into one cluster. Then, for example, these 3 points are in another cluster. We keep on adding the data points into a single cluster one by one. So that's why it is called agglomerative. Agglomerative means combining. Initially, each point is in a different cluster. Then with some criteria, we keep on combining the clusters. Finally, hopefully, what we do is, we combine all of these into one cluster, all of this into another cluster. So this is how we can do in agglomerative clustering. Are you clear with agglomerative clustering, what it does? Initially, each data point is in a different cluster. We keep on combining using some metric or some measure, some criteria, so that we'll keep on getting lesser and lesser clusters. So for example, initially this one is, and this one is in a different cluster. Now what we do is, using some criteria, we'll see if we can combine these two clusters. If we can, we'll keep all of these in one cluster, which means instead of 2 clusters, we got into 1 cluster. Similarly, this one and this one is in a different cluster. Using some criteria, we combine these two. So, and these 3, let's say these are also in 1 cluster. So finally what happens, these 3 are in different clusters. We'll see if we combine these 3 into 1 cluster. If we can, then what we do is, we combine all of these into 1 cluster. Some criteria, that criteria is what that linkage methods are. I have mentioned single linkage, complete linkage, all these things. The criteria is nothing but some linkage method. But we are yet to understand what is this linkage. Are you clear so far? How do we combine?
Yeah, I'm clear until now, Sandeep, but you told based on some criteria you will combine the
Yeah, linkage methods I
individual
did not
points.
mention.
Okay. Okay.
I did not mention. That's what I am saying.
Okay. Yeah, I'm clear, Sandeep.
Oh. Okay. So using some criteria, which is nothing but some linkage method, we will try to combine. Now, what is this criteria? How do we combine? When do we combine? So for that, first we need to understand distance or similarity matrix. So when do we combine some 2 things into 1 cluster? When, for example, this is 1 cluster and this is another cluster. When do we combine these 2 clusters? The only reason why we combine these clusters is, those two clusters are having some similarity. They are having some kind of similarity. Because they are similar, we combine. That is the only reason we combine, right? Clustering is nothing but similarity, grouping similar things together. That's it. So when do we combine? We combine only when 2 items are same. So when are 2 items same or similar? When the distance between them, so if you want to define it mathematically, then we have to say that the distance between those 2 items are less. That's why we combine the clusters, because we already talked, we are all only talking about the mathematics part. So that's why, if you ask, if you are asking me when these 2 clusters should be combined into 1 cluster, I'll tell you that it is only the only reason why you combine is the distance between them is very less. So that's why we go into distance metrics. So 2 distance metrics we know that we will use is Euclidean distance. And there is another distance. Do you remember? Manhattan distance. So we can use one of these distance metrics to find out if those two clusters are similar or not. But the point is, when there is a cluster, this is one cluster and this is another cluster, how do I find out the distance between two clusters? Actually, the distance, Euclidean distance or Manhattan distance, is only a distance between any 2 points. Maybe, for example, one point is this one and another point is this one. This is the distance actually I have to use. I cannot compute the distance between two clusters. I can only compute the distance between any 2 points. So the question is, if you have two clusters like this, how do you find the distance between two clusters with Euclidean distance or Manhattan distance? So that is nothing but linkage method. What linkage method will give you is, it will give you a measure of how to find out the distance between any two clusters instead of points. Are you guys clear why this linkage and all came into picture?
Yes, Sandeep.
Linkage method is a way to find out the distance between two clusters, since Euclidean distance, or for that matter even Manhattan distance, but let's say only Euclidean for now. Euclidean distance can only find out the distance between any 2 points. So Euclidean distance is only giving me distance between any 2 points, but I don't know how to find out the distance between any two clusters. So that's why I want something called linkage method. I want to find out the distance between two clusters using some linkage method. So Euclidean distance can only find out the distance between any 2 points. So I know how to find out the distance between 2 points, but I do not know how to find the distance between any two clusters. That's why I started with linkage methods. Now what are these linkage methods? Well, these are very easy methods. Single linkage method. So to find out a distance between two clusters using single linkage method, what you have to do is, let's say this is one cluster and this is another cluster, and your data point is lying somewhere here. I want to find out if this cluster, if this is each data point is a cluster, right? So this data point is a cluster. This is another cluster. I want to find out if this data point called A can be combined into a bigger cluster like this, or if this data point A should be combined with this cluster. Which cluster is much more similar according to this?
The left side, Sandeep.
Left side cluster, right? Because it is closer to the left side cluster. That's why we are saying left cluster. That is correct. So this A, this point, let's say X. Let me call it as X. This is cluster A. This is cluster B. Which cluster I have to combine with? This X point has to be combined with cluster A. How do you know? Because this is much closer to the cluster A. That's how you are saying. Visually, you are able to say. But in reality, I cannot tell anything visually, right?
Yes, Sandeep. By calculating the distance,
I have to calculate something. What is the calculation I have to use? Single linkage. I have to find out some distance. But distance between what? What and what? There are many data points here. So from all these data points, which data point is the distance I have to calculate? So one way to do it is single linkage method, which is nothing but whichever point in this cluster is nearest to this data point, choose that data point and find out the distance. So let's say this is the nearest data point on this cluster from X. So I chose that one. Similarly, on this cluster also, whichever data point is nearest to this data point, this point X, choose that point and use that distance. Okay. Now this distance is less, this distance is more. So whichever distance is lesser distance, that distance you have to use in single linkage method. Are you clear with single linkage method? In this entire cluster, choose one data point which is nearest to the point of my interest. Similarly, in this entire cluster, choose a point which is nearest to this X point. This is the point. So take a distance from that nearest point to the X, take a distance from that nearest point to Y, so from that nearest point to this point. Whichever distance is getting less, that cluster you have to choose. In this case, this cluster is what I have to choose. Are you clear or not?
Yes, Sandeep. I'm clear, Sandeep.
Okay, this is single linkage method. Now there is something called single linkage, is also called nearest neighborhood distance, or simply you can also call it as min distance. Whichever is minimum distance, that minimum distance I have to take, that minimum point I have to take, and out of those minimum points I have to take another minimum distance. Now complete linkage method. Now what is this complete linkage method? This is also called farthest neighborhood distance, farthest neighborhood or maximum distance. What you are going to do here is, you have two clusters, the data points are looking like this, and there is an X data point here, and here there are another set of data points. Take a point which is farthest in each cluster. So for this X point, what is the farthest point? Maybe this one. This one may be farthest point. So take that data point and take a distance from X. Similarly, on this cluster also, take a point which is farthest from the X data point, which is in this bold. So take this point and take a distance. So take the farthest data point and take the distance from that farthest point. Then you will get some distance d1 here, some distance d2. Then what you do is take a minimum distance out of all the both of these. Out of those farthest distances, which one is the minimum? That minimum distance is what I have to use. Are you clear for this complete linkage?
Yes, Sandeep.
Then there is another linkage method. I think these linkage methods are very easy. I think you might have already understood very easily now.
Yes, Sandeep.
And did you understand why linkage is needed? Because I cannot have one distance. I can have 100 distances. Which distance I have to use? In a cluster, I'll have a lot of points.
Yes.
Now, what is this average linkage? You have an X data point. I think you may guess it easily. What you have to take is, from this data point, take a distance from each of these data points. Every data point you have to take a distance. Then this is called D11, D12, something like that. Average of all these are called D average, D bar, D1 bar. Similarly, here also I'll take all the distances. Take an average of all those distances. That is called D2 bar. Whichever is minimum, the out of both of these averages, that cluster you have to merge the X point with. Are you clear?
Yes, Sandeep.
Okay. Very easy. This topic is very easy. One of the easiest that you can see. Then there is something called centroid linkage. We are already out of time, but let me complete the linkage methods at least. There is something called centroid linkage. What you do, there will be some center point. Center means out of all these data points, you will have some average point. From that average point, you take a distance from X. This is your centroid for cluster A. This is another centroid for cluster B. Take a distance from that centroid data points. Call this D1, call this D2. Again, minimum distance. So if you see, the distance calculation might be different. Finally, which cluster you will say? Out of both the distances, minimum distance is what you are going to do. Even for complete linkage, you are taking farthest data point and taking a distance. Again, farthest data point and taking a distance. But finally, out of these two distances, which cluster you have to consider is something
Minimum
that
distance.
has minimum distance. Always minimum distance, but which point you consider is a different point, a different story. Okay.
Okay.
That is the gist of what we are doing actually. Then finally, median linkage. What is median linkage again? Take a median point. Centroid linkage is taking an average point. This is a median point. This may not be exactly at the center, but median point is going to give you better results. So take a D1 here, D2 here, both from both the median points. Which point, which cluster you have to merge? Whichever
Okay.
cluster is having minimum median, minimum distance. Any questions?
So here you told median, you mean median of all the available data points in cluster.
In that cluster, even
Okay.
centroid is also same.
Yes,
In this
Sandeep.
cluster, what is the average data point?
Okay.
But here we are talking about the median data point within this cluster. Okay.
Yes, Sandeep.
Okay. So those are the linkage methods we are going to talk about. So we'll do a small problem tomorrow and then try to understand the clustering. So tomorrow we will be able to close the clustering itself. It's a very simple topic actually. Okay. Any questions?
Yeah. No, I'm clear, Sandeep. So what will be the practical use case of these linkage methods,
We
Sandeep?
will get into that. We'll get into that. Okay.
Okay.
Okay. Then. So
All right.
I think we are already at the end of the class. So we'll close the session for today now. Okay.
Sure. Okay.
Any questions other than this?
No, I'm clear, Sandeep.
Okay. Okay then. That's all I have for today. We'll catch up tomorrow then.
Sure.
Bye.
Bye.